So you can see my screen, right?
Yes.
Perfect. Okay, so hi everyone. My name is Fatemeh, and my data science capstone project is applications of the statistical inference techniques to neural networks. And I have worked on this project with my advisors, Professor Fiondella and Professor Louhghalam. So the abstract of this project is that neural networks are computationally expensive models. And in this work, we study a small neural network to obtain test statistic that can be expanded for larger networks. We derive the Fission Formation matrix of a neural network, which can be used to obtain test statistic, enabling a statistical hypothesis testing. Experiments are performed on a binary classification problem, and our results indicate that statistical hypothesis testing techniques can help data scientists quantify the significance of a neural network's parameters. So neural networks are among the most frequently used models for classification problems, and their broad usage is preferred to other machine learning methods because of lower generalization error compared to decision trees and nearest neighbor classifiers, while being easier to build than support vector machines. Due to the nonlinear nature of neural networks, we normally apply regularization techniques instead of traditional statistical model selection approaches. This research provides an approach to test the statistical significance of the coefficient in a neural network. So a neural network is composed of linear combinations of neurons organized in layers according to its architecture. The sigmoid activation functions of the neurons can assume various nonlinear forms that determine the intensity of their output. In this section, we actually developed an analytical expression for the neural network so we could later differentiate based on its parameters, which are W, which is the weight, and B as bias. So here, as you can see, I have coded the inputs of each of the neurons, and then we are actually using this input in sigmoid activation function, which will actually result in the Y variable as follows here. And also let me just quickly explain the graph that on the left, we can see the input variables as X, and the X0 is actually defining the bias variable. And in the middle, we have the Z variable, which are actually the hidden neurons in our hidden layer. And at the end, we see the Y variable as the output. And each of the W arrows actually show the weights of each of the neurons. So the loss function. The loss function evaluates how well a machine learning algorithm models the features in the dataset. We seek to minimize this loss, which can be done using a number of optimization techniques. Regression problems often employ mean squared error, while for classification problems with discrete output class, we normally use cross entropy. In our experiment, we can't use UMassD because we need comparable expressions with maximum likelihood estimation. So we use binary cross entropy that is a log likelihood expression and enables us to later apply Fission Formation. So here at the right, you can see the loss function, which is actually the binary cross entropy expression. And then we have actually inputted the Y variable, the Y hat variable that we have coded in the previous slide. For the Fission Formation matrix, we can say that the Fission Formation introduced in mathematical statistics is a method of evaluating the amount of information that a random variable X carries about an unknown parameter of theta of a distribution that models X. It is used to...
要到12点半以后才能做午饭了。
还在考试。
考试是那个。
It is used to calculate the variance covariance matrix related to the maximum likelihood estimates, and it can also be used in the formulation of test statistics. The Fission Formation is the second derivative of the log likelihood evaluated at the maximum likelihood estimate, which can also be expressed as the Hessian of the relative entropy. In classification problems, minimizing this loss is actually equal to maximizing likelihood. So the Fission information can be derived as the Hessian of the loss function. And here we want to talk about the dataset that we have used. So we picked graduate admission dataset to illustrate the methods described in the previous section. It actually consists of 400 observations, and each observation includes the following variables. We have admit, which is a single binary response variable from the set 0 to 1, where 1 and 0 respectively indicate that the applicant was or was not admitted to the university. And we have GRE, which is an integer variable between 220 to 800, indicating the GRE score of the student. And we have GPA as numeric variable between 2.26 to 4, indicating GPA of the student. And finally, rank, which is a factor variable with 4 levels, 1 to 4, indicating the rank of the school which a student has applied to, where 1 represents the highest rank. So for the model validation, there are multiple model validation methods, but we use hold-off validation. And in this method, we randomly split the data into 2 subsets, a training and a testing set. Training was performed with 70% of the data and testing with the remaining 30%. We will use training set for fitting the model, and then we use testing to predict the results. And since this is part of the data that model has not seen before, we can use their prediction result to see how accurate our model is performing. So the neural network results, we have 6 parameter estimates of the fitted model, which actually include the 3 input layer weights and bias, and the weight and bias of the single neuron in the hidden layer, which are as follows. The fitted neural network model exhibited an accuracy of 0.70. For sure, larger and more accurate networks are possible, but the focus of this study was to demonstrate the applicability of statistical inference techniques. So for the Fission information calculations, we used TensorFlow's gradient API for automatic differentiation. After obtaining the neural network coefficients from training, they are substituted into loss function equation, which is actually, you can see it here on the right. And then we then take the sum of this equation evaluated at each data point to obtain a single matrix element corresponding to a pairwise coefficient comparison. This is then repeated for each matrix element to obtain the 6x6 Fission information matrix. And for variance covariance matrix, so covariance matrix is obtained by taking the pseudo-inverse of the Fission information matrix. And the reason that we use pseudo-inverse was that the inverse of the Fission information, actually, we couldn't do that because it was a singular matrix and it didn't have the inverse, so we used pseudo-inverse instead. Off-diagonal elements of the covariance matrix represent the covariance of 2 variates, and diagonal elements represent the variance of the variables. And as you can see, the last 2 variables, which actually represent the weight and bias of the hidden layer, gave us the non-zero variance. For confidence intervals, a confidence interval for an unknown parameter of W estimated by W hat with significance value of alpha contain all possible values for W hat for which we can reject the null hypothesis against alternative hypothesis, which is W not equal to W hat, when performing a 2-sided test. Similarly, we can write confidence intervals for the unknown parameters in our neural network model as follows, where Z of alpha is a critical value for 95% confidence interval, which is equal to 1.96, and sigma of W hat is the standard deviation of W hat, which is obtained by taking the square root of the variances calculated in the variance covariance matrix in the previous slide. And N is the number of points in the data set that the model was trained on, which is equal to 70% of the total of 400 observations. So the confidence interval results actually obtained by substituting each parameter of the neural network in the previous formula, and the following confidence interval table is obtained. This table shows that the 95% confidence interval of all the parameters in our model does not contain 0, which means these parameters are statistically significant. And the 4 first variables actually are highly significant, that their confidence interval actually contain only one number. For the graphical illustration, so the area under the curve from 0 to infinity, which is 0.002, tells us the probability that the output bias parameter is not significant given the observed data. And since it's less than our alpha, which is equal to 0.05, we reject the null hypothesis, and the result, which is the bias parameter, is significant. The significance of output weight is even stronger as of the significance of the input layer weights and bias. And applying this approach with a larger network may reduce the significance of some parameters or actually render them insignificant. So in conclusion, we can say that in this research project, we developed an approach for conducting statistical inference techniques for neural networks to help us in model selection. We can use the expression for cross entropy for a range of neural network designs with having the ability to test the statistical significance of the parameters of each model. And we are actually looking into expanding the neural network model to test and compare our results on larger networks. And finally, this research shows that neural network can also use statistical inference techniques, which will make their results more interpretable. And here are my references. And thank you. And that's it.
Thank you. Any questions from the audience, please?
I do have a question. So you use this neural network for the statistic purpose. Have you compared the neural network results with the traditional way? Is this consistent?
What do you mean in a traditional way?
I mean, the statistic inference technique. If you have some data, then you can use that to test on this hypothesis testing, right? So you train the neural network, and then you use the trained network to deal with that case. And you can also follow the traditional way to get this testing. So will these two results be the same?
Well, actually, when conducting the neural network, we also used, for example, logistic regression to just compare our results to see if, each of these parameters will be significant. And the result that we got from logistic regression also indicated that the parameters of our model are significant. So after conducting this experiment, after gaining the same result, we, kind of certified that our approach is actually resulted in a correct way.
Okay. Since you stopped on these slides, can I ask, so for example, B11, the lower and upper limits are the same. How to understand this?
Yeah, exactly. So I believe that these 4 parameters that we only have like one number. So basically, if you see in the previous slide, so here, the variance of the 4 first parameters are 0. So basically, that's why we only see one number in their confidence interval, which will indicate that these first 4 parameters are highly significant. But the last 2, which had like a variance more than 0, these 2 actually gave us a larger confidence interval. So for the first 4, we could just indicate that these are highly significant parameters of the model.
Okay, I got it. Thank you. It's a very nice talk.
You're welcome.
I have a similar question, actually. The formula that you're showing for the confidence interval largely relies on normal distribution. Can you assume something like this when it comes to weights? Is your sample large enough?
Actually, we also used a larger data set to test this. But as I said, so actually the main purpose of the study wasn't to just build a large neural network. We wanted to, to start with a small data set, because we wanted to, see the applicability of our approach first. So we are currently trying to use actually larger networks, not necessarily larger data set, but actually larger network. So for example, adding more neurons to the layer or even increasing the hidden layers that we have to test and compare with the results. But just increasing the data set wasn't, really helpful in testing the experiment. Neural network architecture itself was like a better measure to, to differ in every experiment than just, increasing the number of data.
I can help briefly with that. The theory of maximum likelihood estimation states that the Fission Information Matrix is asymptotically multivariate normal. So the larger the sample size, the closer to a multivariate normal distribution we get for the marginals.
Yeah.
So I'm assuming that this is how you approximate your weights. You don't need a larger data set. You just need more weight values, I guess.
Yeah, exactly. To just add more neurons, we would have like more weights, more biases. And I have included here that, we believe that applying this approach with a larger network probably will reduce the significance of some of the parameters.
Okay, we don't have time to debate whether we're using normal distribution or a t-distribution. So are there any questions from the panel, please? I know that Leslie already asked the question. We are already running over time on this presentation, but any last questions, please? Okay, well, sorry.
No, that's fine. That's fine. We can move on.
All right, let's thank the presenter and move on with the next presentation, Nikita Seleznyov.
Thank you.